Okay, so on this first learning objective, we talked last class period about identifying some different ones. You have some good examples, amino acids as one set of examples. You could use something like, for strong acids and bases, of course, you could use sulfuric. For weak acids, phosphoric acid is a great polyprotic acid or base system. And just being able to give those examples is adequate. Second learning objective, identify the predominant species in a specific solution showing mathematical proof. So what we just took a look at, we would have been able to assign the concentrations so that you could say which one was the most predominant species, right? So let's see, what problem was that? That was 10.6. So what was the most predominant species in solution from our acid-base system?
The
From 10.
protonated form.
What's that?
The base.
Yeah, the fully deprotonated form, B, was the most predominant species, right? Because it had almost all of the formal concentration still present when we made the solution. Now, this is a fairly complex mathematical way to do it. We're going to take a look in a few minutes, I think during today's class yet, at simpler ways of identifying the predominant species in solution for acid-base systems. And we're going to rely on them being weak acids and bases, and we're going to rely on our understanding of buffers in order to do so. So we'll take another look at that, and you'll kind of have two different ways of approaching it. One that really is pretty purely mathematical, and the other one is based, of course, on our favorite equation, the Henderson-Hasselbalch equation. But we're going to rely on a little bit more of just reasoning through it and doing some diagramming to help us give an answer. So we'll do that in a few minutes. Solve for relevant quantities is the third learning objective. That includes pH, concentrations, pK values. We did some of that last class period. We worked through that example 10-B, I think, was the one that I worked through together with you. I just showed you 10-6. That includes some of that same sort of thing. You did 10-D from the chapter exercises. These are all great examples. This really is just sort of a coverall for, hey, if you need to solve for a quantity, be able to do that. Here's a list of them. The fourth learning objective, calculate the fractional composition of each species in solution. We've done a little bit of this, but I also have, let's see, I think it might be my next problem. No, not the next one, but maybe the one after that. I have, I think, 3 prepped for today, potentially, to take a look at. If we don't get to them all today, we'll come back to them on Monday and finish up chapter 10 then, before we jump into chapter 11. But we will do some fractional composition. Remember, these are our alpha calculations. Finally, describe similarities and differences between mono and polyprotic buffers. So understanding, for instance, that you get multiple buffer regions in a polyprotic system, that those buffer regions are centered around each of the respective pK values. And regardless, we generally define the buffering region or capacity as the region that allows you to withstand up to 1 full pH unit shift, plus or minus from a pK. So those are some real simple values or sort of statistics to be able to draw from in a description of those differences. Drawing a picture, for instance, of a polyprotic system might be useful also. You may not feel entirely comfortable doing that until we've made it through our next chapter, which is our acid-base titrations. Because in acid-base titrations, we're going to spend some time solving for specific pHs at different points along a titration curve so that we can produce theoretical titration curves either manually by hand drawing them and doing the calculations, or as you'll find in one of your homework assignments, it's part of doing it in Excel. You're going to generate an Excel spreadsheet that can produce a diprotic titration curve given pKa1 and pKa2 and given starting concentrations and volumes. It will calculate the volumes and pHs on a 0.1 pH scale or increment, and produce alpha fractions and all of those things. So we'll take a look at that in that homework. Harris goes through it in the text also. So this will kind of carry over a little bit into the following chapter. All right. Any questions about any of these before we jump into trying to address a few of them a bit more specifically?